Hi everyone, and welcome back. So we've been talking about the basics of energy, basics of wave motion so far. So let's talk about transfer of energy. So progressive waves essentially transfer energy, right? And this is something that we're going to talk about a little bit more in the context of stationary waves in the next chapter. So the progressive wave is actually transferring energy, whereas the stationary wave or a standing wave is in fact storing energy. So this is something that I want you to make sure you understand, what is in terms of difference between the two. And again, in terms of progressive, you have transverse and you have longitudinal. So these are essentially like how you would categorize different types of waves in different ways, how they move versus how they transfer energy. So the idea of progressive waves transferring energy is, you can see it with waves on the sea. Energy is picked up from the wind on one side of an ocean, and it's carried across the ocean and dispersed on the other side as the wave crashes onto a shore. So how do you define the intensity of the energy that's being transmitted? So actually the term is quite simply intensity. That is the term that gets used here. So intensity is equal to the energy that's being transmitted over time over a certain area. So that is how, for instance, you measure the strength of the light coming from the sun. I'm saying this in very simple language. It is basically the intensity of the electromagnetic radiation that is coming incident on the surface of the Earth. That would be the more scientifically accurate way of saying it. So this is perpendicular to wave motion. And sometimes in some books you will see it written as the wave velocity, basically, perpendicular to the direction of the motion of the wave. So the intensity is quite simply, what is energy over time? We know this now, right, guys? Like, it's power divided by the area. So it is expressed in watts per square meters. Take it as a given for now, guys, that the intensity of a wave is proportional to the amplitude squared of that wave. Basically, that means if you cut the amplitude of a wave in half, then the intensity of that wave is decreased by a factor of 4. What else do we know about the intensity of waves? Well, if waves come from a point source, then they will spread out equally in all directions. So think of the example of dropping a pebble into water. Then that is actually, I take that back. A better example of that would be a bomb that gets detonated underwater. We've seen examples of that. So that is going to be called a spherical wave. So as the wave travels further and further and further from the source, the energy it is carrying passes through an increasingly large area, right? What is the surface area of a sphere? So let's say you had a point source there, right? And imagine this in 3 dimensions. I'm drawing it in 2, but imagine this in 3 dimensions. You have, after a certain point, the wave that's carrying the energy from this explosion is going to be in this first circle, and then after a little bit more time, it'll be at a circle that's a little bit more outside, and then a little bit more outside, right? Than that. So the surface area is increasing over time of the sphere the spherical wave that is carrying this energy. So the surface area of a sphere is equal to 4 pi r squared. And as a result of that, the intensity of the wave is decreasing with increasing distance from the source. And in fact, it is decreasing in the inverse proportion of the square of the distance from the source. So these are 2 relationships that you should understand, that intensity is proportional to the amplitude squared, and then inversely proportional to the square of the distance from the source of that energy. let us now look at another topic, which is not directly related to wave intensity, but is related to sound waves themselves. And that is, how do you go about measuring the frequency and the wavelength of sound waves? The reason, guys, it might feel a little bit jarring to go from wave intensity to frequency and length of sound waves is because there is a topic here on stationary waves that I'm actually deferring to chapter 15. Because I think, in my opinion, the syllabus is not organized in the correct manner. Stationary waves deserve to be talked about as a whole by themselves, and I'm going to do that as part of chapter 15. So I'm taking some material that is related to stationary waves in chapter 14, and I'm going to be talking about it in chapter 15 instead. So bear with me. Let's move. I know it's going to be a little bit of a whiplash, but let's go to a different topic, which is an experiment. And we're going to talk about frequency and length of sound waves and how do we measure those. So guys, recall, sound waves are longitudinal waves, right? And vibrations of particles in this kind of wave, in basically air particles in this kind of a sound wave, will produce areas of pressure which are slightly higher, which are called compressions, and then slightly lower, which are called rarefactions. So slightly higher than average, slightly lower than average. That's why sound waves are often described as being pressure waves. So how would you measure the frequency of a sound wave? So the best experiments I've seen on this are basically something that use a cathode ray oscilloscope, right, which is attached to a microphone. And what that microphone is trying to receive is there's going to be like a loudspeaker over here, connected to some kind of like a signal generator. So it might emit just a single tone or something like that, right? So it's the microphone is trying to listen for what the sound speaker is generating as a signal. So the period of the wave, how do you determine that? Well, you got to set the time-based setting on the microwave, and you gotta measure the number of waves that are being shown on screen, right? So I'm going to write this down here so that you have this for later. But you basically, guys, if this is not ringing a bell, you need to go back and watch the videos that we did. I think it was chapter 2 or chapter 3, where we looked at time-based settings and voltage, the Y sensitivity on a cathode ray oscilloscopes. So you can let's work through an example. So let's say, for example, I'm setting the time-based setting at 5 milliseconds per division, right? So can I calculate the frequency of this wave? And let me actually draw a wave for you here. So I'm going to use a different color. Let me use the color red here. So in this case, you have like, maybe something that looks like that, right? So you have, I'm going to assume that I didn't draw it quite well, but let's just say for the sake of argument, you have 3.5 waves. I know it's not 3.5 in the picture here, but let's say you have 3.5 waves, because I ran out of space and I didn't want to draw it in a way that you couldn't see. So you have 3.5 waves in 4 divisions on this oscilloscope. So in a case like that, well, let's use a different color. How many divisions did you have? We had 4 divisions, right? So 4 times 5 milliseconds per division from here is equal to 20 milliseconds. And the 20 milliseconds has 3.5 waves. Okay, so that's one thing. What is the time period of the wave as a result of this? Well, the time period of the wave is going to be 20 divided by 3.5, which is equal to 5.7 times 10 to the minus 3 seconds. And what is the frequency? Frequency is just going to be 1 over t, which is going to be 175 hertz. So you just figured out the frequency. Can you figure out the wavelength? You absolutely can, because you have set it up, right? You can measure how many divisions there are. So you should be able to see what the wavelength is here as well. Now, I want to also point out one thing to you. Use as much of the screen as you possibly can to reduce these uncertainties, right? And the wavelength, and I apologize, I didn't say it explicitly, but the wavelength, you can look at the screen, is going to be the wavelength from one peak to the next peak, or from one trough to the next trough. Again, use as much of the screen as you possibly can to reduce the uncertainties, right? So that brings us to the end of this particular video. In the next video, we're going to talk a little bit about the Doppler effect, and I'll also quickly touch on the electromagnetic spectrum and how that works with the wave motion. So I'll see you in the next video.